Calculating RLAC series circuits. This is where we get into the mathematics and the actual number crunching of how we solve these circuits. Let's take a look. First things first, let's get some numbers in, and then we'll start crunching out some values. 120 volt AC source, 60 hertz, 20 ohm resistor. And it's going to be connected in series with a 530 millihenry inductor. And this inductor, I'm just going to put in brackets here, is pure. And what that means is that there is no resistance to the inductor. The significance of that will become apparent on our next example. First step, sketch the circuit. Yes, I know you don't want to, and I appreciate that, but I'm telling you, you have to if you want to get it right. So here is my circuit. I'm not sketching the entire thing because we all know this connects back to my source, so who cares? Why would I sketch the entire thing? Now what I'm going to do is indicate all of the properties for each of the individual components. This is the resistor, that's the inductor. So let's start with Q. There would be VARs for this inductor. There would be a voltage across this inductor, a current through the inductor, an XL of inductive reactance. What about the power factor of the inductor? All right, let's move over to the resistor. The resistor will have Q? No, it will have P, power, watts. There will be a voltage across the resistor, a current through the resistor, and a resistance, as the French say, of the resistor. Over here, I'm going to do totals. This is for the total circuit. Totals are going to include S total. What about E total, I total, Z total? Why is it Z? It's Z because I'm going to have a combination of both resistance and inductive reactance. And then finally, power factor total of the whole circuit. May as well add power factor here too. Bit of a foregone conclusion. Next step, step 2. So why don't we even list them? Look, I'll even list them. Sketch. Step 2, fill in known values. All right, so fill in known values. Known values are things that have been given up here. So let's see, 120 volts, that would be the source. 20 ohms, that's the resistor. XL, no, don't go there. It's not 530 millihenries, is it? 530 millihenries is the inductance of the inductor, which means you need to take the 60 hertz and apply it to the inductance to get the inductive reactance. So for us to calculate the inductive reactance, we need to use our formula, which is XL is equal to 2 pi FL. 2 pi FL will equal, well, 2 times pi times 60 times 530? No, come on, 0.530. Gives me 199.8 ohms. Ohms of what? Ohms of inductive reactance. Whoops, why am I writing 188? 199, sorry, 0.8 ohms. We're going to take things to approximately 2 decimal places with most of our calculations. If you take more, that's fine, but really it shouldn't make a huge difference to our outcomes. All right, so we filled in our known values. 3. Now we're going to start calculating. And I'm going to say, let's start calculating values that we already kind of know or that we can work with. So I've got voltage, I've got ohms of resistance and ohms of inductive reactance. What's the first step? Well, there really is not a whole lot of opportunity for me to choose different directions of accomplishing this question. If I want to know anything about either of these, I need to know the current that flows through the circuit. What is the current? And if I want to know the current, I need to know what is my impedance. Impedance is going to give me my answer for the total amount of ohms that I can then have rushing through the circuit. So Z total is what I want to calculate, and Z total, let's do an impedance triangle. I'm going to do it over here. Yeah, no, I'm going to do it right here. Impedance triangle. All right, so the impedance that we are working with, I have a horizontal and I have a vertical component. There's going to be a hypotenuse. The impedance is a product, while using a little bit of Pythagoras, of my in-phase component, 20 ohms, and my out-of-phase component, 199.8 ohms. This is XL and this is R. So 199.8 squared plus 20 squared equals, and then we square root the whole thing, 200.8 ohms. This is my Z. Z, 200.8 ohms. So if I've got 200.8 ohms, I could probably write that over here, 200.8 ohms. Now, if I have voltage of the whole source and I have impedance of the whole source, then I should be able to work out current of the whole circuit. So we're going to use Ohm's law. Ohm's law is ohms and volts, right? So I is equal to E over Z, 120 divided by 200.8. That gives me a current value of 0.59. I'm going to take it to 3 decimal places, amps. 0.597 amps. Great. Okay. Well, let's head over here. Can we use this information? Yes, it's a series circuit. Whatever the current is here is the same here, 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 all the way along. So that means that 0.597 amps. 0.597 amps. Once I know the current value for this circuit, can I now calculate the voltage and the relative power? In the inductor's situation, it would be VARs. In the resistor's position, it would be watts. So what process do we go through in order to calculate that? You have a choice, but I'm saying let's make this easy. If you know the resistive ohms and the current, can we not just use our calculation I squared times ohms? Okay, I squared, so 0.597 squared times 20. That gives me a total amount of watts, right? Total amount of watts of 7.128. What about the voltage across the resistor? The voltage across the resistor would be Ohm's law, 20 times 0.597. That gives me 11.94. What about on this side? Well, I've got ohms and amps. Can I just work out the volts? Sure. So let's use Ohm's law. Ohms times amps. So 0.597 times 199.8 gives me 119.28 volts. Could I use these two numbers here to work out the VARs? For sure, because we know that the current through the inductor times the voltage across the inductor should render the VARs stored and released to the inductor. So 119.28 times 0.597 gives me 71.21 VARs. Now, what would be the power factor of these two individual components? Well, the power factor would be for a resistor 1. It'd be a power factor of 1 because we know that there is no reactive component. What about for the inductor? The power factor should be 0, and we would say it's 0 lag because there's no in-phase component. Okay, so we've worked out all of this, and now we're over here on the totals. I still have two pieces of unknown information. What is the S total? Is in the total VA of the circuit. The total VA of the circuit is going to be equivalent to using a power triangle. So let's do power for the whole circuit. Same thing, we're going to do a horizontal and a vertical. What is the Q VARs? It's 71.21 VARs. What is the P watts of power? 7.128 watts. Hypotenuse, that would be S, and that will give me the VA. So let's calculate this. I'm going to use Pythagoras with these two values. 71.21 plus 7.128 squared, square root of the whole thing, 71.56 VA. Does that make sense? It has to be bigger than any one of the other sides. Not by much, but it is. Good. So that's 71.56 VA. Now, could we have calculated that just by taking the total voltage of the circuit and the total current of the circuit? And the answer is yes. This, using Pythagoras, is going to give us the same value by working with the power and the VARs as simply Ohm's law would up here. These are the totals for the circuit, which means if you take the total current and the total source voltage and you multiply them together, which is one of our power formulas, we should come out with almost the exact same value. And I come out with 71.64. So what I want you to realize is that there are two different methods to calculate many values throughout a series RLC AC circuit. And they will render slightly different values. The difference in these values is what we say negligible. We were looking at a difference between 71.56 and, which was Pythagoras, and I worked out on my calculator with a power formula 71.64. So this was a power formula. Okay, the difference between these two values matters not. I'm going to say here, don't worry, be happy. Okay, there is no significant difference between those two values, and we will find this as we go through many calculations. There will be numerous times where there will be multiple ways to approach a question and to calculate every single value, and they will differ slightly depending on the method chosen. Of course, the more decimals you take, the closer these values will become, but they will never be precisely the same. And so I just want you to realize, don't lose sleep over this. It does not matter. It is not something that we are worried about, and you will not receive a failing mark on a question on an exam simply because you are off by this value, which is significantly lower. Remember, all exams are multiple choice, and because of that, the answers will be obvious, and the difference between your calculation and my calculation will not be a problem. As in, I will not have these two answers on the exam. That would just not be fair. All right, that aside, let's look at the power factor. The power factor of the entire circuit. The entire circuit, what is the power factor of it? We said the power factor is a product of the in phase and the total. Well, we did a impedance triangle of the total circuit and a power triangle of the entire circuit. That would mean that I should be able to look at the angle between the in phase and the horizontal and the hypotenuse. And so I have two triangles to choose from. The wonderful thing about using triangles in Pythagoras and trigonometry is that for the circuit, since these are totals, the ratios that are represented should be exactly the same. As in, it does not matter which of the two triangles you choose to use in order to calculate the power factor. Let me show you. We could calculate the power factor by taking the impedance values. So power factor could be equal to, we could do a calculation of 20 divided by the hypotenuse, 200.8. 20 divided by 200.8 gives me 0.09. Let's calculate the power factor from this one. This one we're using power in watts divided by the VA, which is the hypotenuse. So 7.128 divided by 71.56. 7.128 divided by 71.56. That gives me 0.09. So what I want to draw your attention to is that it's the same. It does not matter which triangle you choose to utilize in calculating the power factor. This angle will be the same for both, which means the power factor will be the same no matter which one you use for calculation. So we end up with a 0.09 power factor. Now, we need to indicate when we have a power factor that is not 1, right? When it's a power factor of 1, we all know that this is unity and that it is only resistors that we're referring to. When we have a power factor that's something other than 1, we need to indicate it if it is either inductive or capacitive. And in this case, it's pretty obvious. It is inductive. So we say the word lag. Lag. This is a power factor of 0.09 lag. Now, what is the phasor diagram for this particular circuit look like? How could we identify it? Well, let's take a look at the values that we were given. So the phasor diagram is going to be the current value, and the current value we had for this circuit was 0.597. So I'm going to do it in black. I total equals 0.597 amps at, remember, this is a series circuit, 0 degrees. The next one I'm going to sketch in here is the voltage for the resistor. So the voltage for the resistor is 11.94 volts. So V of the resistor equals 11.94 volts at 0 degrees. What about the voltage of the inductor? Remember, the voltage of the inductor is much longer, and I'm not drawing this to scale, but you get an idea. It is certainly larger, and it is going to be vertically up here, isn't it? So here is make it as long as I can. This is voltage of my inductor, which was 119.28 volts at 90 degrees. So the last thing that we're missing here is then our source voltage. I understand it is 120 volts, but where is it going to be? And so what we need to do is add these two vectors together, and we can work it out that way, or we can use the power factor of the circuit. So two different methods for sketching source value. So I'm going to say for source volt, either add phasors, and that would be with an HV table or mode 3. So add the phasors together, right? Or use power factor. Okay, well, we've already sort of looked at how we add phasors together, and we know how HV tables work. You would take this phasor, work out the horizontal and the vertical component. You would then take this one, work out the horizontal and vertical component, and then you would add the verticals and the horizontals together and work out what the new vector was. If we use the power factor, that's kind of taking into account power factor of total circuit, I should clarify. That's kind of indicating that we already know the magnitude. The magnitude is known if we are going to choose this route. It's 120 volts. And all that this power factor is going to do is it's going to determine the angle for us. So that's all it's going to do, determine the angle for us. And the angle that we're going to be looking at here is going to be a product of using our trig. So we're only going to calculate the angle. So how do we do that? Well, cos of the angle is equal to power factor. And an easy way for us to then get immediately to our answer, angle is equal to the power factor with the inverse cos applied. So our power factor of this circuit was 0.09. So 0.09, now apply inverse cos to it. And the way that you're going to have to do this, the process, is we're going to have to do the way that your calculator requires it. Enter inverse cos first. And then after you've entered in inverse cos, you're going to enter in 0.09, which is our power factor. And we end up with 84.83 degrees. (84.83 degrees). This angle is referenced from 0. As in the reference line. And so if we were to sketch it, remember, we already know what the magnitude is. The magnitude is already known. It was given to us, 120 volts AC, and all we were calculating was the angle. Well, now we can sketch that in. The voltage of 120 volts, it should be approximately the same length as this one, because it's 119.28, right? So I'm going to sketch it with a different color just so we can distinguish between the two, and it's at 84.83 degrees. So let's take a look at the Cartesian plane. This would be 90 degrees, and this would be 0 degrees. That would be about 45. So, I mean, my source voltage is very, very close. It's going to be up here, isn't it? So this would be E total. Oh, it doesn't turn out very well. I won't use this marker much more. E total is equal to 120 volts at 84.83 degrees. And I'm just going to go over that with a pen because you can barely even see it. E total is equal to 120 volts at 84.83 degrees. So the phasor diagram looks like this. We have more of a lagging or inductive circuit. We calculated the source voltage angle by using the power factor. And when we went to sketch the combined value, we had a choice. We could have added the phasors together, and in doing that with our HV table or mode 3 on the calculator, it would have given us both the magnitude, 120, and the angle, which was 84.83 degrees, right? That's the angle right here. All right, so that brings us to the end of our first example of how we combine values for a series RL circuit. We're going to do a few more examples to give you an idea as to some of the differences and how we sort of combine values in different ways.